Hello everyone. In this section we're going to, for the, I guess probably the final time depending on how many we cover, we're going to do one more linear programming problem formulation class. Similar to what we did last time with different problems. The reason is we need a solid understanding of how the natural language problems or the natural language system relates to mathematical language. Only when we have both a solid understanding of both are we able to adapt what we see in natural language and convert it to the language that we require to solve the problems. The pizza problem we'll solve next time because I want everyone to have a chance to work on it before I post the solution. So let's move on. Today, the first one we're looking at is the crumb and custard bakery example. The crumb and custard bakery makes coffee cakes and pastries in large pans. The main ingredients are flour and sugar. There are 25 pounds of flour and 16 pounds of sugar available, and the demand for coffee cakes is limited to 5 cakes. 5 pounds of flour and 2 pounds of sugar are required to make a pan of coffee cakes. 5 pounds of flour and 4 pounds of sugar are required to make a Danish. Coffee cakes have a profit of $1 and Danish has a profit of $5. How can the bakery maximize daily profit? Generate and solve a linear programming problem to determine how many to manufacture of each. So this is a pretty standard question. There's not a lot that's new and interesting. So let's open a new slide. And as always, let's review our problem and highlight the key information. So the crumb and custard bakery makes coffee cakes and pastries in large pans. The main ingredients are flour and sugar. So we have ingredients, we probably suggest those will be constraints that we have to deal with. There are 25 pounds of flour and 16 pounds of sugar available. So again, this directly relates to what we just talked about and will most likely be the limitation governing how much we can make. The demand for coffee cakes is limited to 5 cakes. 5 pounds of flour and 2 pounds of sugar are required to make a pan of coffee cakes. Five pounds of flour and 4 pounds of sugar are required to make a Danish. Coffee cakes have a profit of $1 and Danish have a profit of $5. So we've highlighted all of our key information. One thing that we have to check when we're doing problems of this nature is we generally want to have an idea what our correct answer might be. So let's look a little more carefully here. 5 pounds of flour and 2 pounds of sugar are required to make coffee cakes. 5 pounds of sugar and 5 pounds of flour and 4 pounds of sugar are required to make a Danish. These are almost identical. We see here that both require 5 pounds of flour, and Danishes do require a little more sugar, but we see here that they're significantly higher in terms of profit. So most likely, when we solve this problem, and we won't do that today, we're only going to formulate the problem, but if we were to solve this problem, we would most likely see very few coffee cakes made. Coffee cakes require almost the same resources, but have only 20% of the profit that Danishes have. So most likely, Danishes are going to be the choice that we make in this situation. That's most likely the way we're going to go. So how can we maximize daily profit? All right, let's begin formulating our problem, not profit. They make coffee cakes and pastries. That's what we're trying to determine. So X1 equals coffee cakes, X2 equals pastries. And again, when we create our objective function, we have to see how these coffee cakes and pastries relate to income or profit in this situation. So coffee cakes have a profit of $1 and Danish have a profit of $5. So we can go here, maximizing Z of profit is equal to 1x1 plus 5x2. And this is profit per coffee cake plus profit per Danish. That's all we've done so far. Next up, as before, we want to list our constraints. And our first one, C1, let's go back here. We see that there are 25 pounds of flour and 16 pounds of sugar. That's almost guaranteed to be two separate constraints. So let's do the first one, 25 pounds of flour. And the 25 pounds represents the maximum flour available. Here we see it's 5 pounds of flour to make a pan of coffee cakes, 5 pounds of flour to make a Danish. So again, we come back, and it's very simply 5x1 plus 5x2 greater than or less than or equal to 25 pounds of flour. 5 pounds of flour for a coffee cake, 5 pounds of flour for a Danish must be less than or equal to our total amount of flour available, which is 25 pounds. We do the same thing for C2. We see we have 16 pounds of sugar available, so that becomes our maximum. And then we have to check how much sugar is used for each. So we have 2 pounds of sugar for a coffee cake, so 2x1, and 4 pounds of sugar for a Danish, 4x1. So 2x1 plus 4x2 less than or equal to 16 pounds of sugar. These are our first two constraints. We also have one more, so let's review. The demand for coffee cakes is limited to 5 cakes. We saw earlier when we initially reviewed how many cakes we'd probably make that coffee cakes aren't very profitable. So it looks to me like coffee cakes have a profit of $1, Danish have a profit of $5. Looks to me like in this situation, we're not going to get near our coffee cake limitation of 5 cakes because we're going to spend most of our resources making Danish. It's similar resources and much more profitable. But because it's listed here, we should list it in our constraints. So x1, C3, x1 is less than or equal to 5. And that's max demand for coffee cakes. So we've completed our question very simply. It was very similar to what we've done before. And as you can see, the questions will get more complex. There'll be more decision variables. The questions will get more complex. There will be more constraints. But most of the time, the type of constraint that we see will be predictable. Until we get to much higher level questions, these are relatively predictable. So let's do our full question formulation. All right, as we move to higher levels, and this is not exactly a higher level, but the key is formulating these questions. If you're able to formulate the questions effectively, and we've done that here, using Microsoft Excel or QM for Windows, management science focused computer programs, solving these problems is very easy. And the way this relates to service operations management is everything is about efficiency. If we are efficiently making choices, we're efficiently using resources, and that guarantees greater competitiveness and greater profitability for our organization. Two critical goals. So, moving on. We're going to do several questions today. Now again, this is a relatively simple problem, but let's go through it together because a lot of these questions, while similar, require a set way of thinking, and that's what we're trying to develop here. A formulaic approach to problem solving. That's our primary goal right now. So we read the question. A jewelry store makes necklaces and bracelets from gold and platinum. The store has 18 ounces of gold and 20 ounces of platinum. Each necklace requires 3 ounces of gold and 2 ounces of platinum, whereas each bracelet requires 2 ounces of gold and 4 ounces of platinum. The demand for bracelets is no more than 4. A necklace earns $300 in profit and a bracelet $400. The store wants to determine the number of necklaces and bracelets in order to maximize profit. Formulate a linear program model for this problem and solve it to determine the optimal manufacturing choices. I'm going to give you right now about 8 minutes. I will come back in 8 minutes. Again, I won't actually wait 8 minutes. I will continue almost immediately, but I will give you 8 minutes to solve this problem. It is nearly identical to the previous one. When I come back, I will solve it very quickly, but I would like you to take the time now to try to solve it effectively because it's almost the same as what we just solved. This will be included in the PPT uploaded with the YouTube link later, with the YouTube link I give. So let's take a quick break, 8 minutes. I would like you to solve this problem now. All right, everyone, welcome back. I assume that you paused the video for some time until you were able to attempt to solve the problem. All I have done is solve the problem without walking you through it step by step. Those 8 minutes hopefully were enough time, and it should be enough time for you to process problems like this. You will have similar problems on your final exam. They will be numerous. So they are things that you will have to attempt to solve relatively quickly because it is a time limited situation and this is something that you will have to sort out in the future. So very quickly, because I've given you the time to solve it, necklaces and bracelets are X1 and X2. We're trying to maximize profit if we get $300 for a necklace and $400 for a bracelet. Our first constraint is gold available. We see it's 3 ounces of gold for a bracelet, a necklace, and 2 ounces of gold for a bracelet. And that's 3x1 plus 2x2 is less than or equal to 18, the total amount of gold available. We also know from here that we have 20 ounces of platinum available, a necklace is 2 ounces of platinum, and a bracelet is 4 ounces of platinum, represented here. 2x1 plus 4x2 is less than or equal to 20, which is the platinum available. We also know the maximum demand for bracelets is no more than 4. X2 bracelets must be less than or equal to 4. Collecting all of the information together, we get this final representation of the problem stated in equation format. Correctly modeled problem formulation. Hopefully everybody was able to achieve that. It is, as I said, a very simple problem and very similar to the the crumb and custard bakery problem we did earlier. There should have been no problems. Hopefully everyone attempted the problem. If you are not attempting these problems, it will be difficult on the final exam, so please attempt to finish these problems whenever possible. All right, as we continue on, we're looking at another problem, and that's just essentially what we're doing. And this may seem repetitive, but the key is finding the correct problem-solving process and applying it to a variety of problems. Some of it is very straightforward. Other problems require a little bit more complex thinking because there are variations. So let's look next at the Valley Wine Company problem. The Valley Wine Company produces 2 kinds of wine, Valley Nectar and Valley Red. The wines are produced from 64 tons of grapes the company acquired this season. A 1,000-gallon batch of nectar requires 4 tons of grapes, and a batch of red requires 8 tons. However, production is limited by the availability of only 50 cubic yards of storage space for aging and 120 hours of processing time. A batch of each type of wine requires 5 cubic yards of storage space. The processing time for a batch of nectar is 15 hours, and the processing time for a batch of red is 8 hours. Demand for each type of wine is limited to 7 batches. The profit for a batch of nectar is 9,000, and the profit for a batch of red is 12,000. The company wants to determine the number of gallons of 1,000-gallon batches of nectar and red to produce to maximize profit. This question isn't very different from what we've seen so far, but the key here is there are more constraints than we're used to at the moment. So let's look carefully. They produce 2 kinds of wine, and I gave you a hint at the bottom, X1 and X2. These represent X1 and X2. So let's do a new slide, begin our problem formulation. Because X1 and X2 were given to us, we can skip or we can immediately enter that here. Problem formulation 7. X1 is, we see here, Valley Nectar. X2 is Valley Red. So let's go back. The wines are produced from 64 tons of grapes. This is a resource, most likely a constraint. A batch of nectar is 4 tons of grapes. A batch of red is 8 tons. So we have our first constraint essentially. Production is limited by the availability of only 50 cubic yards of storage space, another limitation, and 120 hours of processing time, a third limitation. So we know already we're going to have 3 constraints. A batch of each type of wine requires 5 cubic yards of storage space. So this relates to storage again. Processing time for nectar is 15 hours, and the processing time for red is 8 hours. This relates to time. So we still have 3 limitations so far. The first one is grapes, the second is storage space, the third is time. All information so far has related to that. Demand for each type of wine is limited to 7 batches. So here we have limitations 4 and 5. Our limitation for the first batch, nectar, and our limitation for the second kind, red. Both are maximum of 7. The profit for a batch of nectar is 9,000 and the batch of red is 12,000. So now, even before we've started writing anything, we know our objective function. It's how financially our decisions relate. And we also know that we have 5 different limitations. So we can go to our sheet and we're going to change it. Well, we're not going to change. We're going to go max z, because we're still trying to profit, equals 9,000 x1 plus 12,000 x2. Very simply. We also know that we have not 1 or 2, but 5 constraints. So C1, C2, C3, C4, C5. So what we've done is we're beginning to formulate the problem, but already we know there's going to be 5 constraints. So let's go back and look at our first constraint. We have 64 tons of grapes, nectar is 4 tons, red is 8 tons. Very easy. We have 4x1, which is tons of nectar, plus 8x2 tons of red, less than or equal to the 64 tons we have available. That's our first constraint, given to us in the first 2 lines. Now we look at the second constraint. We have 50 cubic yards of storage space, and we have 50 tons of cubic storage space. A batch of each type of wine requires 5 yards of storage space. So each one, x1 and x2, will be 5. And we have only 50 cubic yards available. So very simply, 5x1 is less than or equal to 50, which is storage space available. Our third constraint, we go back and we check. We have 120 hours of processing time. Processing time for a batch of nectar is 15 hours. Processing time for a batch of red is 8 hours. So again, we have all of our key information. Nectar is x1, so 15x1. red is x2, plus 8x2, less than or equal to 120. So 15x1 plus 8x2, less than or equal to 120 hours, and that's manufacturing time available. So here we see that we're in a situation where we've completed 3. Number 4 is a little less clear. Demand for each type of wine is limited to 7 batches. If we do x1 plus x2 less than or equal to 7, that doesn't work because each one, x1 and x2, is a maximum of 7. So what if we do x1 plus x2 is less than or equal to 14? Again, this doesn't work because that means x1 could be 14 and x2 could be 0. So we need 2 different limitations. x1 is less than or equal to 7, which is demand for nectar. Oh, and x5, we have x1 is less than or equal to 7 again, which is demand for red. That's what we've shown so far, our demand for each. So we have a total of 5 different constraints. Same thing we've done before, just with slightly more constraints. So we'll open a second slide and we'll collect all of the information together. So we have x max z equal to 9,000 x1 plus 12,000 x2, subject to C1 equal to 4x1 plus 8x2 less than or equal to 64. C2 equal to 5, it's not equal, sorry. It's just a base heading. 5x1 plus 5x2 less than or equal to 50 yards of storage space. C3, which is time, 15x1 plus 8x2 less than or equal to 120 hours. C4, x1 less than or equal to 7. C5, x1, x2 less than or equal to 7. Taking all of this information and plugging it into any managerial science computer program, as stated, will allow you to solve very easily this relatively complex question. Okay, so one more time, we're going to move on. We're going to wrap up with this one, and I'm going to give you about 10 minutes. This one's a little more complicated, but it is important because it does require you to think a little bit. So in 10 minutes, please pause your video for 10 minutes because I will come back almost instantaneously. I want you to attempt to determine essentially how to formulate this problem. It will be almost instantaneously for me, but for you, I'd like you to pause the video and try to solve this on your own. So let's take a short break, and when we come back, I'll present you with the correct solution to this problem. All right, everyone, hopefully you paused the video and you were able to complete this problem. Let's look at it quickly together because you've already theoretically completed it. Shirt Shop makes t-shirts with logos and sells them in retail stores. It contracts with two different plants, one in Puerto Rico, one in the Bahamas. These are our decision variables. Where will we manufacture shirts? X1 is Puerto Rico, X2 is the Bahamas. The shirts from Puerto Rico cost 0.46 cents and 9% of them are defective and can't be sold. The shirts from Bahamas cost 0.35 cents. They have an 18% defective rate. So 35 cents, 46 cents, 35 cents. These represent our costs. And because it's cost, we're trying to minimize. Companies don't like spending money if they don't have to. That's what we're doing here, is we're minimizing Z this time. So we know that 9% are defective in Puerto Rico, 18% are defective in the Bahamas, and 88% have to be saleable, so not defective. We do that here. 0.91 X1, so 91% of X1 and 82% of X2 must be greater than or equal to 88% overall, which is our minimum defective rate. We found the 0.91 and the 0.82 from the 9% defective and 18% defective. We know we need 3,500 shirts, so X1 plus X2, the total ordered must be 3,500. We know we have to retain its relationship with the two plants. It wants to order at least 1,000 shirts from each, and that's what we've indicated here. X1 must be more than 1,000, X2 must be more than 1,000. So with this basic information, slowly, hopefully, you're now able to very quickly and very easily interpret these questions into the proper model format. So to wrap up today, you'll have one final homework assignment here, Copperfield Mining Company. Each of them, and I'll allow you to do it on your own. The key here is you'll have 3, in this situation, I want you to put together your correct number of constraints, your correct number of variables, and we'll look at this again next week. Thank you everyone for listening. Hopefully, if you took the time to properly format or properly solve these problems, you're at approximately the correct 45-minute time period. Thank you again. I will upload everything at the exact same time this morning.